Now let's talk about Le Chatelier's principle. Hopefully I pronounced that correctly, but I like to think of this principle as sort of the homeostasis for reactions. So I put homeostasis for reactions. Now, why do I think of it as a homeostasis for reactions? Well, it's because I'm more of a biology person, so I like learning about anatomy and stuff, and I'm also pre-med, so that also is part of why I understand homeostasis. And homeostasis is just the body's way of balancing and reacting to different situations. For example, we sweat in order to lower our temperature. So when we sweat, we're basically, every time we sweat, that water has heat. So sweating is a body's mechanism of reducing the body's heat so we can maintain our temperature. And when it's cold, we shiver so then we can generate energy in order to sort of increase our temperature. And that's homeostasis. It's this balancing factor, and it's like the equilibrium of the body. So Le Chatelier's principle is like the homeostasis for reactions, where it has to be in balance. And any stressful situation that occurs, and we're going to talk about some of them, like increase in temperature or concentration, there will be some sort of mechanism that will happen in order to bring that reaction back to equilibrium or back to balance. So, Chatelier's principle, homeostasis for reactants, and this only applies when we're in equilibrium. Obviously, because Le Chatelier's principle is responding to different stressful situations when in equilibrium. So, Le Chatelier's principle only applies when a reaction is in equilibrium. Now, let's talk about what factors can sort of affect Le Chatelier's principle. And I'm going to just color code these. First one I'm going to talk about is concentration. So concentration. Now when I'm talking about concentration, I'm talking about reactant concentration and product concentration. And let's say if we increase the reactants, well, we already know what's going to happen because this is just QC being less than equilibrium constant. So an increase in reactants is going to result in a shift to right. So the reaction is going to shift to the right in order to balance equilibrium, in order to bring the reaction back to equilibrium. Now, if there were more products, then we'd see the opposite, where the reaction would shift to the left. Shift to left. And this is because we have more products. Think of the seesaw example. We're having more products or more weight on the right-hand side versus the left-hand side. So to balance that, we need to add more stuff to the left-hand side in order to bring that back to equilibrium. So that's concentration, and if we had like less reactants, it would shift to the left. If we had less products, then shift to the right. So it's sort of, you can think of it as vice versa. Now, that's for concentration. So what about, and let's talk about temperature. So how does temperature affect? Well, the only way temperature can affect a reaction, or the only way that a reaction responds to it, is if it's exothermic or endothermic. So let's have different colors here. So I'll just say exothermic, and let's see, what color do we want to do? I'll do this one, endothermic. Well, what is the difference between the two? Well, we've talked about, or actually we never actually have talked about this, but exothermic reactions are basically when heat exits the system. So it's like releasing heat. And one exothermic reaction is basically when we sweat, because we're releasing heat in order to get back to normal temperature. And that's an exothermic reaction on the human body. Endothermic would be like us kind of shivering, where we're trying to develop heat. Or another way of you can think of endothermic is when you're trying to maybe heat up a cake, maybe you're trying to bake a cake, that heat is going to go into the cake in order to change the proteins and whatnot in order to sort of bake the cake. And exothermic might be something like you're trying to freeze some water, so heat is going to escape, and that's when we see a change from liquid to solid phase. So exothermic, heat is exiting; endothermic, heat is entering. So that's like the simplest way of understanding it. And we really have to know if it's exothermic or endothermic in order to know how temperature affects it. So exothermic reactions are always going to end up as a negative enthalpy. And let's just put kilojoules per mole. So our units are going to look like this. And if it's negative, then it's going to be exothermic. But if it is endothermic, then we're going to have a positive enthalpy. And let's actually, I'm just going to draw a graph real quick showing this. So what we have here is when we have an exothermic reaction, we're basically going from, let's just say this is our reactants. So we're going from here, and as you can see, we see this sort of dip. So we're going from maybe like from 3 or something to -1. So we're basically decreasing, and that's why we see a negative enthalpy, because it's a negative change in. But if we do the opposite, going from, oh, that's actually a weird one, going from up here and going from here. So reactants over here, products over here. Let's just go with the 0 and 3 over here. We have a positive change. And these are just like random numbers I'm just throwing out just to illustrate what endothermic and exothermic looks like on a graph. But we can see this positive change. And that's why endothermic is positive, because we're gaining heat energy. So now that we know that, let's actually draw some reactions and see how what I mean by that exothermic and endothermic. So let's say we have simply A goes to B. Let's just say plain out, or actually let me change this color real quick, and let's just make it white. So we're gonna have A goes to B. A's are basically our reactants and B's are products. And if it is exothermic, then this guy over here is going to be placed over here, because we have that negative heat. So we have a negative change in heat. So we just put it on the product side. And if we increase temp, I'll just put temp just to say temperature. So if we increase temp, then we're putting more weight on this side, on the product side. So we need to increase our reactants, and that's why it shifts to the left. Shift to, let me change that, shift to left. And same thing for the opposite. If we decrease temperature, so let me actually scroll down a little bit more. So if we decrease temperature, then we're shifting to the right. And this is because we have less products now. There's a little bit more weight over here, so we need to shift to the right to counterbalance that. Now let's look at an endothermic reaction, and we'll have the same A goes to B, but our enthalpy over here, and let me just actually copy this. So our enthalpy will be right here on the reactant side when it is endothermic. Actually, let me just move this over here. So our enthalpy is going to be on the reactant side. And pretty much same logic. I mean, all you really have to do is just draw out where it's going to be, where the enthalpy is going to be. So if it's endothermic, it's going to be on the reactant side. If it's exothermic, it's going to be on the product side. So now if we increase temperature, so let's just say we increase temperature, then we're adding more stuff to the reactant side, so it needs to shift to the right. And if we decrease temperature, well, we're having less of the reactants on the side. We're having less stuff on the left side. So when we decrease that temperature, then we're just going to have to shift to the left in order to counterbalance that. And that's pretty much how temperature and increase in temperature, whatnot, can affect equilibrium. But it's all based on if the reaction is exothermic or endothermic. Now, what about volume? So volume is actually a really interesting one. And volume is more, it's really going to relate to pressure. So when you have, and obviously this is just a review for some of you guys, so if you have increase in volume, we have a decrease, and let me actually change this to a different color. We have a decrease in pressure. So, and let me actually change this to an equal sign. So when we increase volume, we decrease pressure, and let's say when we decrease volume, we increase pressure. And this is just, I think it's one of the laws. I forgot, maybe Boyle's law or Charles' law, but we increase pressure. Now this pressure part is very important because you have to know the relationship between volume and pressure, and they are inverse. When volume increases, pressure decreases. When pressure increases, volume decreases. So that's very important to know in order to understand how pressure affects equilibrium. So now that we know that, then let's go back to our arbitrary example of A to B. But in these cases, you're gonna have to look at the moles of the reaction. So when it asks you like a decrease in volume or increase in volume, look at the moles of the reaction. Look at those stoichiometric coefficients. So in this example, we have 2A goes to B. And the reason why this only applies when there's a disparity in gas moles is because Kc equals Kp when we have the same amount of moles. So this equilibrium constant is going to equal the pressure equilibrium constant when we have the same amount of moles. So now let's look at an example of how an increase in volume can affect the equilibrium. Now when we increase volume, we obviously decrease pressure. And when we decrease pressure in this reaction specifically, then our reaction is going to shift to the left. Now, why is this? Well, usually when we increase pressure, whichever side has the most moles, we're going to go to the opposite of that. And it's kind of like I think it's kind of hard to explain it, but I think of it like this. So if we decrease pressure, then we have to resort to something else to counterbalance that. It's kind of like if we bring up like a medical example, if we have high blood pressure, we need something to counterbalance that. We need something to bring that down, which we could say like it's a statin or something like that. So if we have a decrease in pressure, we need something to counterbalance that, and that's where those moles of gas come into play. And in order to counterbalance a decrease in pressure, we need to increase the amount of moles. So we need to go to the side that has the most moles. So when we decrease pressure, we need to go to the side that has the most moles in order to bring that back to equilibrium. And the opposite is true for decrease in volume, because when we increase pressure, then we're going to shift to the right. Because we already got an increase in pressure, so we need less moles in order to counterbalance that. This is literally like pluses and minuses. So the plus will counteract the minus. So if it's like maybe a positive one and a negative one, we need that counterbalance to become zero or just equilibrium. So that pressure is an increase, so we need something to counterbalance that, and we have less moles. So bottom line here is that with a decrease in pressure, we need to go to the side with the most moles, and increase in pressure, we need to go to the side with the least moles, just to counterbalance that pressure and bring us back to equilibrium. It's sort of like alleviating the conditions or the consequences of pressure. So to alleviate that, we need to go to the place with the most moles if pressure is high, and if pressure is low, we need to go to the place with the most moles. So like we said, just alleviating, it's counterbalancing. You have to understand this about Le Chatelier's principle and equilibrium, where it's always a counterbalancing act. It's always maybe like good versus evil, that yin and yang. It's always trying to bring it back to equilibrium. Whatever happens, we're trying to do the opposite in order to get back to ground zero. So hopefully that helped, and as always, a Pomodoro a day will make you a doctor someday. I'll see you guys in the next one.